Yeah.
Okay, guys, so let's start. So last time I started to explain decoders. So decoders are actually one of the very popular or widely used. They are very widely used in the digital system circuits, logic circuits. Okay. Today also I will teach multiplexer. Okay. I'm going to show you both of them right now on the same slide because they are very close to each other. Okay, so let's see. I'm going to make a comparison between decoder and multiplexer. So, okay, so let's decoder here, and then here we have multiplexer. Okay, so in case of a decoder, as I told you before, it's a logic circuit. If you have inputs, how many outputs you are going to have? So if you have here n, so I should have here 2 to the power of n. For example, if I have here x and y, if I have two inputs this way, so I should have 4 outputs this way. Four outputs this way. Is that okay? If you have n inputs, if you have a number with n bits, okay, how many different numbers you can represent? 2 to the power of n. Yes. This is because every number in the input here. So if you have x and y, if you have only 2 inputs here, how many numbers you can have here? 4. For every number, we have 1 pin here, 1 output for everyone. So here, this is pin number 0. That means when the input is number 0, this pin has to be 1. All the other pins should be 0. You got what I'm saying? So always one output is 1, and the other outputs are zeros. That's how it works, okay? So if the input is 0, this is the one that has to be 1. 1 here means, I explained last time, it has to be active, and active can be 1 or 0. But here I'm teaching, assuming it's active high, okay? So, so here, this is pin number 1, is 1, 2, and 3, okay? So based on what number you have here, so the corresponding output here is gonna be 1, everyone else is 0. Make sense? Any questions? This is how it works, okay? So that's what we call decoder, okay? What about multiplexer? I want to teach them together because you will see right now, they are too close. Even the design, even the internal design is too close, okay? So I like to do something like that because if you understand one, it's easy to understand the second one because they are very related, okay? Anyway, let's talk about what is multiplexer, okay? In multiplexer, number 1, we have here only 1 output. All the time, yes, we have only 1 output, okay? Okay. And now we have here inputs, we call them selectors. We call them selectors. And then how many, and then we have several inputs here. Okay. So this selector is if you have any selector, so the number of inputs here I have should be 2 to the power of n. No? So here I have any selectors, okay, and I have 2 to the power of n inputs. And I have only 1 output. You can see here, before even we explain more, you can see there is a similarity between them. Here you have n 2 to the power of n. Same thing here, I have n 2 to the power of n, but I added 1 output here more. Yes. Okay. So how this one is working, how it works, and why there is a relation between these two. Because always when you find the relation of something like that, n and 2 to the power of n, that means all possible cases, all possible numbers. That's true. Look here how it works. The way it works is, actually the multiplexer here, it's like a switch, okay? So it's like here, we have like a switch here, okay? So the output here, it's like you have a switch here. So here, let's have an example. If you have here two inputs, that means 2 selectors, okay? So that means I have 4 here, okay? So here, this one I'm going to call it input number 0, input number 1, input number 2, input number 3. Is that okay? And then it's like a switch. I have a switch this way. So if I put here in the selector, if I put number 0, 0, for example, so the output here, the output will be connected to I0. That means the output will equal to the input 0. It's like I have a switch. That means, let me say it in a better way. The output here should equal I0 or I1 or I2, IR3. Who's going to decide if the output is equal to I0, I1, or I2 or I3? Who's going to decide? Selector. You got what I'm saying? So if the selector is equal to 1, number 1, so actually here the output should equal to I1. It's like you have a switch, for sure, this is imaginary switch. In reality, all of these gates, but what it does, it's like selecting. So here, what we do here, the output here should equal whatever I have here. Equal means, what it means equal? It's very easy. If the input is 0, output is equal to 0. If I connect the output to I1. So whatever you have here in I1, 0 or 1, you will see it here. Okay, you see the difference between both of them? So one of them here have in inputs have 2 to the power in output. Based on the number you have here, the number you have here should be active, assuming active is 1, and all other inputs should be zeros. That's how this one works. For the other one, it's like a switch. Switch means we have only one output, and this output can equal I0 or I1 or I2, I3, equal whatever is there, whatever value is there, 0 or 1 for sure, okay? So, and this selector is gonna decide if I select this one or this one or this one, okay? So that's why you can see the relation here. If this one is in, this one has to be 2 to the power of n, okay? Because all possible cases I have here, for example, in case of 2 inputs, I should have 4 cases. It means I have 4 selections. That means I should have 4 inputs here. You understand? That's why the relation here has to be, if it is n, it has to be a 2 to the power of n. Is that okay? Any question here? You understand? Now, here, number 1, guys, you should understand how the logic circuit is working, how it works. Okay? For sure, you will understand or you will see how can we use it. This is something different. How can we use it? Something different. Okay. Also, you need to know how we will design it. Okay, but in the beginning, you need to understand how it works. Any question here? You see the difference between them? The reason I'm teaching both of them together, because as you will see right now in the design, they are too close. You will see right now. Anyway, so you remember last time when I explained how can you design decoders, I told you for each output here we have one end. Do you remember? Yeah, we said I have here one end, and then here we have output 0. Okay, I'm gonna call it D0. Then I have another end here, and I have here output 1. I have one end here, output 2, and then I have one end here, and this one is output 3. That's what I explained last time. Okay, so here this one has to be 1. This one has to be 1 when the input is number 0. That's why I'm gonna input here the midterm. Midterms. I'm gonna go back to chapter 2, last part of chapter 2, the midterms. That means I'm gonna put here x prime, y prime. X prime, y prime, which is actually 0, 0. This is M0. This is a midterm 0. Okay? When you have input is 0, 0, in order to get 1, so it has to be x prime, y prime. Okay? In case of number 1 is this way. Okay? Assuming this is x and this is y. Okay? So here, this time it has to be x prime, y. And for this one here, this is midterm 1. Okay? Here, if it is number 2, okay, so this one has to be x, y prime. Okay, this is midterm 2. This one here is actually when x, y equal to 1, 1, so it has to be x, y. Very easy, very, very easy. Okay, so that based on I just link things together. When I explained the midterms, I told you based on the input, only one midterm is 1, all other terms are zeros. Okay, that's exactly what happens here. So only these 2 should, if the input is 0, 0, so I find here 1, 1, and then there should be some zeros here. Okay, at least one of these should be zeros. Okay, that's why I'm for sure I will get zeros here. Because in case of n, if only one input is 0, I can get 0. Okay, same thing if the number is number 1, 0, 1 here. Okay, so x prime y, this is the only 2 that are going to give me 1, 1. That's why I will have here 1. For the other ones, there should be at least 1, 0. 1, 0 here, 1, 0, 1, 0 here. Okay, that's why we get zeros. Very easy. What I'm saying? So here I explained a very simple decoder, and this decoder actually 2 to 4. Okay, I can design any other decoders. I can design 3 to 8. It will be exactly the same thing, the same way. The same, everything is the same, but I'm gonna have here 3 inputs and I'm gonna have 8 outputs, 3 to 8. You got what I'm saying? Also, I can design 4 to 16. Whatever you can design, this is something, this is the design. You can design whatever you want to design. You understand what I'm saying? Any question here regarding this part? Okay. Let's look at this part. You will find something very similar. Look how I'm gonna make it, okay? That's why I'm teaching these two together, because this is the best way to link them together. This is gonna help you to understand it. But let me see if I can use a different color. Okay. So let's see how I can design this one here. Okay. Look at the idea. I'm gonna copy this part here. I'm gonna put it here. You will see right now. Okay. So here I'm gonna say we have here x prime, y prime. Okay. And then I'm gonna put here I0, input 0. So it's the same thing like this one, but I put here I0. Same thing like this one, I'm gonna put here I1. Same thing like this one, I'm gonna put I2. Same thing for this one, I'm gonna put I3, input 3. Why? Why you are doing that? I'm gonna tell you why. Because if the selector 0, 0, the decoder is telling me it's gonna be 1, 1. 1, 1, right? So it's gonna be 1, 1. If the decoder is 0, 0, I will get 1, 1. And then here I have X or Y. Sorry, I'm gonna call it I0, whatever you call it, I0. You know, if you have 1, 1, I0, the output should equal to I0. This is how AND works. Okay? This is the main point. But if you look at the other ones, for sure, based on as I taught here in decoder, when the selector, here I call it selector, here I call it input. So selector here like an input here. When the input is 0, 0, as I explained here, if it is 0, 0, so I'm sure I have here 1, 1. But for the other ones, I'm sure at least one of them is 0. So there should be regardless, everyone else will give me 0. I want to choose the similarity between them, okay? So yeah, so this is for I0, okay. Same thing if I want to do I1. So I will take these two again, X prime Y, I1. So that when the input is number 1, if the selector is number 1, these are the only two that's going to have 1, 1. And the other ones, I'm sure there should be 0 somewhere, and they will give 0. And the output here will be I1. Okay? Very easy. It's the same thing. I just put one input here. That's it. The same thing. Okay? Here, same thing here. You have x, y prime. I'm going to put x, y prime. And then I'm going to here put I2. Same thing here. Here you have x, y. And then I put I3. And then I'm going to connect everything together. Okay, thanks. I'm going to connect everything together using OR. That's it. Please take a look. Please. This is the best way I can teach this part. Okay, if you can understand. Because this is just a simple modification to the decoder to do something different. Before I take this question, I'm gonna say something again. Let's say give you an example. If this, let me use a different color. So let me give you an example. If, for example, if the input, just to understand what I'm saying, but you can try it in different numbers. So for example, if the selector here we call it selector, which is like input here. Anyway, so if the selector here is actually 1, 1, which is number 3, 1, 1. Okay. So this one is 1, this one is 1, the output here is I3. Because in AND 1, 1, I3, I will get I3. If you look at the other ones, for sure, here I have 0, 0. For sure, this one is 0. At least I have one of them 0. Okay? I have it 0. And for AND, it is enough to have one input 0 in order to get 0. So what I'm going to get here, 0, 0, 0, I3. And this is I3. Whatever the value of I3, 0 or 1. If I3 is 0, I will get 0. If I3 is 1, I will get 1. Okay, let's look at another example. For example, if this one is if the input here is 0, 0, okay, or x prime x is 0, y is 0. So here I'm gonna get I0, and there should be zeros on the other one. So always, all ends give you zeros, and only one end will give you I0. The input, corresponding input. It's the same thing like here, but the difference here, all of them are giving 0 except one giving 1. Okay? Here, all of them giving 0 except one that is giving the input. Yes, your question.
On the multiplexer, did the I0, 1, 2, or 3 be higher bit count? Like, could it be like a 2 or higher than that if you're selecting it to pass through?
Yeah, this is a very good question. So the question is, can I1, I0, I1, I2, I3 can be like a 8-bit number? Every one of them is a number, 8-bit number, okay? Here I'm teaching a selector, I'm teaching a decoder that the input is only 1 bit here, okay? But what you are saying is very valid. For example, sometimes I have here some storage units, we call them registers. This is a part of computer architecture. This is how we can do it in computer. So here I have a register A, register B, for example, register X, whatever. I have a number of registers. And then I want to select one of them to send it to the ALU to do addition. This is how computer architecture, okay? So in this case, I can have a multiplexer here. The multiplexer here, for example, has 8-bit number, and 8-bit number, for example, 8-bit number. And then the output here is going to be also 8-bit number. It's going to go to the addition, the other, to do addition. So now I want to select one of these numbers. Either I want to send A to the other, or I want to send B to the other, or I want to send X to the other. Okay. In this case here, I'm going to have selector. If I put 0, 0, for example, so actually I'm going to put number A here. Number A is going to go to the other. Okay. Yes, you can design something like that, but it's not going to be. I will show you how can we do it. Okay. So I have one example to show how to do it. Okay. But here I'm only focusing on bits, bit. But I can just twist this idea a little bit to make it something like that, because actually that's what usually we do in computer architecture. Usually you have different storage units, and based on the assembly instruction you have, I want to add, for example, I want to add to number A to number 3. So the hardware has to select this one. Or you want to add B, so hardware has to select this one. So we can design it this way, so that the input, but to design this one, I will make it out of this one. But there is an example regarding to this part. But what I'm teaching here only for one bits. But I can extend the idea as there is one example to do that. Any questions? You understand the order together? Very simple. It's almost the same thing, but I just did very little modification. Okay. So just let's go to, yeah, so that's what I explained last time. Also, I explained something interesting last time. It's about enable. Usually, in logic circuits in general, in logic circuit, usually we like the idea of enable or disable. Enable or disable like a switch. You turn it on or off. You can say, you want it to work or not. This is something very desirable, or something we like it in computer architecture, because I need to have control in the devices, because without such a control, all of them are going to work at the same time. I have a control. You should work right now, or you should not work. So even if you have an input, you are not going to work. If disabled, if enabled, you are going to work. So I should have such a control. That's why, in general, usually in logic circuits, we like to have something like that. Anyway, so that's what I did here last time. You have one input here, we call it enable. If the enable is 0, so the outputs are 0, 0, 0, and this one is disabled. Regardless what input you have here, I always get 0 is not working, it's disabled. But here, if you put here 1, now it's going to work normally as a decoder, normally. If the input is 0, 0, so this one is 1, and then you have 2 zeros, and so on. Is that okay? And actually what I did, it was something very simple. All what I did, if this is a decoder, I just added one more input here. That's what I said last time. I added just one input here for, yeah, as you see here, I just added one input here for the enable. That's it. So that if the enable is 0, so by this way, I'm going to put here every gate is going to have 0, 0. So all of them are off. I'm not off, sorry. All of them is going to give output 0. That's what I mean. Okay? So regardless of what input you have, regardless what input you have, all of them are going to give zeros. Okay? Very interesting, right? Yes.
So in a way, the difference between the multiplexer and decoder is the decoder just has all of the selectors fused into one wire.
Okay.
Using the enabler.
Regarding architecture is very close, okay? Regarding what each one is doing is something different. This one is like a switch. I want the output, I want to connect the output to one of these input. It's like a switch. Okay? This one is not a switch. This one is actually is gonna give me the midterm. This one, it has to tell me if the input number 7, so pin number 7 has to be 1, and all other ones should be zeros. You got what I'm saying? So regarding architecture, I can say they are very close, but regarding functionality, they different. Because here this is like a select to be select. Here there is no selection. You got what I'm saying? This one is used. This one multiplexer is used if in case you want to select. As I give you the very good example I give you here, for example, if you have multiple sources of data, and now based on the instruction I have, the hardware has to select this data or this data or this data. So this is how it is. Okay. Also, I told you every time in general, not only in decoders, in any logic circuit, when you see the enable this way, this one means it's active high. You need to be familiar with these symbols. If you see something like that, that means the enable is active high. Active high means if you want to enable, it has to be 1. You have to put 1. You want to disable, you put 0. However, there is another way I can do it, just by putting a bubble here. So if you see an enable with a bubble, again, this is not in decoder only, this is for any logic circuit. Every time you see enable and you see a bubble this way, that means this enable actually is active low. Active low means in order to enable the decoder, I have to put 0. Okay? You need to be familiar with this thing. And actually, what I have to do here is very simple. All what you have to do here, I'm going to just add inverter here. That's it. Okay? So that when I add inverter, when I add 1, so 1 here means it is disabled. 1 means it is disabled. Okay? So 1 here, this one is going to put 0. If this the inverter will get 0. By this way, all of them are zeros, it is disabled. You got what I'm saying? But if I put 0, 0 here means enabled. 0. So actually this one becomes 1. And then now if you have 1 here, and you already know this is in if you have here, if you have 1 and you have x, I will get x. If you have here 1 and you have x and y, so you get x and y. You got what I'm saying? So this one, it doesn't do anything if it is 1. But if it is 0, I will get 0. This is how AND works. Any questions? Okay, good. And then also last time I explained in some decoders, we have bubbles here. That means this one is active low. That means the one that is selected, or the one if you have number 0 here, so this input actually is 0, right? And everyone is 1. So this one is called active low. Okay. It's very important if you look here at if you see the truth table here, you see here. Look at this part here. If E is equal to 1, if E is equal to 1, this is the meaning of it. If E is equal to 1, that means the decoder is disabled. Okay, so regardless what you have here in X and A and B, X here means regardless, it doesn't matter, whatever is there, it doesn't matter. Okay, so here all of them becomes 1s, 1, 1, 1, 1. Okay, 1, 1, 1 here, it means nothing is selected. Because here 0, when it is 0, this is the one that's selected. Okay, because 1, 1, 1, nothing is selected. But in case of active high, it's actually 0, 0, 0, nothing is selected. Okay, now if you look at this part here, because the enable is 0, now it's going to work normally. It's enabled. So now if the input is 0, so this 0 is 0, everything 1 else is 1s. If it is number 1, so here D1 is 0, everyone else is 1, and so on. Any questions? Here it's exactly the same thing, but what I did here, this one was for 3 to 8 to decoder, 3 to 8. Everything is the same. Okay. But just here in case, if you have 3 inputs, that means I'm gonna have eight cases. I'm gonna have here 8 cases, okay? And based on the number, for example, if the number here is number 5, so if I come here, this is number 5. If the input is number 5, I will find D5 here is 1 and everyone else is zeros. Okay, guys, any questions? Yeah, okay. So this is 3 to 8. You can, whatever you can do 1 million to the power of 1 million. You can do that. You can say, because this is something designed. You can design it whatever you want, okay? Any questions? Okay. Let me tell you something interesting here, because I'm going to use it shortly. Look here, guys. I'm not sure if it is true or false to say, can I say this output is actually min term 0, and this output is actually min term 1, and this output is actually min term 2, all the way until min term 7. That means if the input is 0, so this min term 0 is 1, all other min terms are zeros. Can I say something like that? You got what I'm saying? Yeah, it's something like that. So based on whatever you have here in the output, okay, if you may be a little bit confused because the word meter, we use it with functions, if you have a function, okay? But you will see right now, one of the ways, for sure this is not one of the ways to use decoder, but this is not the only way for sure. Decoders can use it for too many things, but one of the ways I can use decoder is to implement any function. Okay, I will show you shortly. But anyway, just I want you to have this observation. If you have a certain input, you can see the output here like min terms. The min terms are given to you. What do you mean by min terms? I mean, if the output here is min term number 5, I would find this one is 1. So just this one is going to tell me the input is number 5. Okay? Anyway, shortly, I will show you how can we use a decoder to implement any function we did before, any function, you will see. But anyway, this is the design of this one. Again, nothing is new. You can see this is the min terms. If you go back to chapter 2, by the end part of the last part of chapter 2, these are the min terms, right? And then after that, I explained how can you do some tricks. Okay, so one of the tricks here we did, if you have 2 decoder, each one is 2 to 4. Okay, 2 to 4. How can using 2 decoder, 2 to 4, how can you make 1 decoder that is 3 to 8? Okay, look at the trick. If you understand, with the help of the enable for sure, with the help of the enable, because in case here you are talking 2, this one has 2 inputs, but here we have 3 inputs. Okay, so here, so this one is equivalent. This one is equivalent to a decoder 3 to 8. Yes. So what is the third input? Because every one here has 2. The third input will go to the enable, as you will see here. Look how can we do it, and what is the logic behind it? Okay, look here. Number 1, I should have 3. I should have three inputs. Yes, input E. Okay, and then here, as you see, X and Y. E, X, and Y. This is the 3 inputs you have. Okay. I'm gonna connect X and Y here and also here, as you see here. So here, that means the same number X and Y is gonna be applied in both of them. And then I will use this one, E, to only enable one of them. Okay. So in general, because here I give you example 2 to 4 to make 3 to 8. But this, okay, just let me finish and we'll take your question. Okay, but this idea can be extended to anything else, but the idea is the same, or the way we combine them is the same. So the idea is, I have 3 inputs, E, X, and Y. I'm gonna take 2 inputs, I'm gonna apply them here. And the last one here, I'm gonna use it to enable only one of them. So if you look at, the best way to understand here, this part is, if you look at here, if you look at the table here, here, look. Yeah, I'm gonna make line this way. In this part, enable is 0. This part, enable is 1. In this part, I'm gonna have numbers from 0 to 3. In this part, for x and y, I'm gonna have numbers from 0 to 3. Okay? Because what happens when E is 0, so actually here E is 0. So this one is disabled. So in the first part here, this one is disabled. But this one is enabled because this one is 1. So in the first half, that's why you see here E is half and half. In the first half here, I'm gonna turn on this one, turn off this one. In the second half, I'm gonna turn off this one, turn on this one. Is that okay? And then based on numbers you have here, I'm gonna select one of 4 values here. I have here 4 values. I'm gonna select one of 4 values. That means these 4 values should be, look here, number you have here, number 0, number 1, number 2, number 3. So that's why I'm saying the 4 output here has to be from 0 to 3. Look here, because we have 0 here, 0, 0 and 0, 0. Okay, we have here D0, we have here D1, we have here D2 and D3. Okay, look here. If you input 0, 0 and 0, so don't think about this one. This one is 0. So I'm gonna find this one is 1. Okay. If I input here 1 here, because this is number 1, because it's x and y. So this is number 1. Okay. So I will find this is the one. I'm gonna select this one. I'm gonna select the second one, and this all the time this one is 0. Okay. But if you look at the second part here, okay, when E is 1, so now I'm gonna repeat everything again, but I'm not gonna, this one is disabled, this one is enabled, so I'm gonna work on this one. And now, when the input is 0, 0, 0, 0, and 1, this is now number 4. So we have 1, 0, 0, this is number 4. That's why here, the first one here, I'm gonna call it number 4. Okay? Before this one was 0. That's why 0, 0, 0 is number 0. So let me look at this one. Look here. When it is 0, 0, 0, so here it should be number 0. But when it is 1, 0, 0, so here this one is 1, this one is 0, 0. In both cases we have 0, 0 here. But in the first case, here we have 0. So that's why here D0. Okay? It should be this number 0. And D0 here is 1. The first output here is 1. But if I put here 1, so now I will find the first one here. That's why you can see sequence. Here, D0, D1, D2, D3, and then D4. D4 after 3, 4. Yes, question.
So when you combine two 2x4 decoders, don't you like lose the enable pin that a normal 3 to 8 decoder would have?
Here, I have 2 decoders that are 2 to 4. Okay, using these 2 decoder and using one inverter, how can you create a decoder that is 3 to 8?
Well, I know that, but what I'm saying is like, it's like in a normal 3 to 8 decoder, it would have the X, Y, Z, and then the E.
Yes.
But this one doesn't have that.
Yes.
Okay.
This one doesn't have E. Yes.
Okay.
Okay. Unless, this is a very good question. So in a normal decoder, 3 to 8 decoder, I have 3 input, I have 8 output, and sometimes, not all, I think always, but sometimes this is something optional. You can add enable or not. But I think most of the real circuits they add enable. Okay, you can add enable or not. Okay, sometimes we have enable, but we have a problem here. Here we did not have an enable. Yes, you are okay that using 2 to 4 we created 3 to 4. You are okay with that, but we don't have an enable. That's your problem, right? Okay, that's why usually what we do is, listen to me because that's what I'm going to do shortly. Some decoders don't have only one enable. Some decoder can have 2 or 3 enables, and this is the decoder that you are going to use in the coming lab. So, for example, if you have here a decoder and I have 3 enabled this way, I'm going to call it enable 1, enable 2, enable 3. What it means? It means in order to enable this decoder, it has to be one, and all of them should be enabled. In order to, not only one, okay? So here I have 3. So in order to enable this decoder, the 3 enabled bit should be enabled. That means I have to input 1, 1, 1. Make sense? And not only that, sometimes some enable make it active low and some of them active high. So if you have a decoder, something like that, okay? So in this case, in order to enable this decoder, this input has to be 1, 1, and this one has to be 0. Anything else, it is disabled. Anything else is disabled. If you only disable one input or one enable, it is disabled. Okay? And that's what I will do very shortly right now. Okay. So in this case, if I have another enable, and that's what I will do shortly, that means if you have another enable, I'm going to call it, for example, E1. So in this case, I can connect here E1 here with E1 here, and I can use this one as an enable for 3 to 8. Not input. So now I have 3 input this way, and I can use this one as enable for 3 to 8. Is that okay? So that if I put here 0, so both of them are off, nothing is working. You got to think, if I make this 1, 1, now this one can decide which one I have to select. Okay, similar to what I explained. Same thing, I can extend the idea if you have two 3 to 8 decoders, as you see here, 3 to 8 decoders, how I can make 4 to 16. 4 to 16. It's the same idea. In case of 4, so now I have here W, X, Y, Z. So again, I will use the last one here because you have half and half. Remember, I can use the last one here as an enable, as you see here. Okay? And the 3 inputs here are going to be input here, and also the same ones are input here. So that always one of them on at a time and the other one is off. There is no way to make all of them, both of them on at a time. There is no way. That's why to guarantee something like that, I have this inverter. This inverter can guarantee there is no way to get 1, 1 here or 0, 0 here. There is no way. Okay? So you cannot enable both of them because of this inverter. Always I guarantee whatever you have here is going to be inverted here. Is that okay? So this is exactly the same thing like here, but I just make it bigger. Any questions? By this way, if the inputs are numbers from 0 to 7, you will get them from the 4 outputs here. If the input is number from 8 to 16, you will get them from the 8 outputs. Any questions? Okay, here I want to show you sometimes if you have a decoder, you have here 4 inputs. Usually, how many outputs you have? 2 to the 4, which is 16. Sometimes I don't need all the 16. For example, if this decoder, the input is BCD. You remember when I said the input is BCD? BCD means the input should be a value from 0 to 9. Because it's a binary number, it's a decimal number stored in a binary number. Okay, but that's why it has to be from 0 to 9. That is why, if you see here, this is how the circuit looks like. I will come the last one here. This is number 10, number 9. So here, number 10, number 11, number 12, whatever you are here is not gonna be, I'm not gonna use, okay? So what output you will get here, it doesn't matter because it should not happen, okay? So if I put in number 15, 1, 1, 1, 1. So whatever output you get here, I don't care because it should not, here you remember when I talked about don't care, something like that, okay? So that's why here, I will stop only at 9 because here the input should be BCD, okay? So it's actually here, I think, yeah, so I think, sorry, this is number 9, 9 is here, and this is number 10. So at 10 or any other number, you will get 1, 1, 1, 1, okay? That's how it is designed. But anyway, this is not the main point, that's what I'm teaching here. So what I'm teaching here is the input here has to be a number from 0 to 9, okay? I'm not gonna take the whole numbers from 0 to 15, only 0 to 9, okay? Yeah, this is how you can design it. This is normally similar to what I did before exactly, okay? Yeah, so again, in exams and anything, please don't draw this way. In exams and anything, to make it easy for me, you can see here the input here, for example, you can tell me A prime, B prime, C prime, D prime. This would be much easier for me to, and it's even much easier for you. And instead, because what happened last semester, there was a lot of lines, and I have to follow the line where this line is going. So it was very hard for me, even hard for you. Okay, so I'm doing this way because if you want to connect the circuit, you have to connect it this way. But in exams, in anything, if you just tell me A prime, B prime, C prime, I know already. If you want to get A prime, you are use inverter, so you don't need to show me too many lines. Okay. We have a chip, and this is the chip you are going to use. We have a chip. This is the chip you are going to use in the coming lab. We have two chips here. One chip is 139, 130. This is the chip you are going to use in the coming lab. So this chip actually has two decoder inside it. So one chip, inside this chip, you have two decoder. These decoder are 2 to 4 decoders, okay? So here, for example, these are the numbers, the pin numbers. These are the pin numbers as you see here. So here, this one, it has two separate decoders, separate. So you can, similar to when you had a chip and you have, for example, 6 inverters. You can use one, you can use two, you don't need to use all of them. Same thing here. The chip has two decoder, you can use both of them, they are separate. There is no link between them. Okay. So this is the first decoder here. You can see here this decoder is active low, is active low. You can see here. You can see the out, this is the output is 4, the input is 2, and it has one enable this way. This is the enable. You can see the enable is active low. So if you want to enable this decoder, so here you have to input 0 here to enable it, okay? And this is what you can see. No, this is a truth table for the other one. There's a small difference between these two, but let's. No, this is something different. But anyway, so let's talk about this one first. Okay, this is 139. This one is 130. That's what you are going to use in the common lab. Okay, so these are two separate decoders that are 2 to 4. This one has only one decoder that is 3 to 8. One decoder that's 3 to 8. Okay, anyway. So yeah, so the second decoder here, this is the second decoder. If you want to use it, you have 2 inputs, you have 4 outputs, and also you have here 1 enable. This is the enable, and this enable is active low as well. Any question here before I move to the next one? Okay, okay, let's move to next. That's what we will use in the coming lab. 138. So let's see how it works, and that's something interesting. I have just explained as well right now. So this one is only one decoder, one, not two. Okay, this is different from this one. This is 138, and so 139. This is 138. Okay, if this one has only one decoder. This is 3 to 8. Okay, this is the 3 inputs are here. The 3 inputs here, A, B, C, which is pin number 1, pin number 1, pin number 2, pin number 3, and we have 8 outputs as you see here, and outputs here. These are the pin number here, and these outputs are active low. Active low. Okay. On top of that, this one it has three pins, enable pins. So here 3 enable pins. I have just explained how it works, right? 3 enable pins. That means in order to enable the chip, you have to enable all of them. If only one of them is disabled, the whole decoder is disabled. Okay, that means if I want to enable this decoder, this pin here has to be 1. This pin has to be 0, this pin has to be 0, because this enable pin is active high, active low, active low. Any questions? Let's see how the truth table here. This truth table will reflect what I said right now. Look here, guys. If one input is disabled, here, G1, in G1 here I put 0. 0 is disabled. Regardless of anything, regardless of what you have here, regardless of what you have here, the decoder is disabled, and all of them are ones. Very easy, right? Very easy. Also, same thing here. If I disable this one, I put 1 here, which is G2A. If I put here 1, if this pin is disabled, regardless of what you have pins in the other pins, regardless, is disabled. It's not gonna work. Okay. One more thing. If this one is disabled, if I put here 1, also the same thing. Everything is disabled. You can tell from the table. Okay. Now, here, this is when it is enabled. This part here when it is enabled. To enable it, you have to put 1, 0, 0. So I have to put here 1. You have to put 0, 0. Now it's going to work as a decoder, 3 to 8 decoder. You can see here, When the input now, so here all of this is the same. 100, sorry, enable. 100, you enable. Now if the input is 0, bin number 0 is 0, and everyone else are ones. When it is number 1, bin number 1 is 0, everything else is 1. When it is number 7, bin number 7. Okay, output number 7 is 0, everyone else is 1. Any questions? Easy, right? Now, regarding your question, okay, because this is a coming slide. Regarding your question, if I have 2 of this one, if I have 2 of this one, can I create? So you have here 3 to 4, 3 to 8 decoders. Can I create one decoder that's 4 to 16 with enable? That's what I will do in the next slide. You get what I'm saying? So I will use 2 of this one. So as you see here, so what I will do, look here how it works. Okay. The idea is that, okay, so here I want to make 4 to 4. So in case of 4, so I should have here W, X, Y, Z in case of 4. Okay, number 1, X, W, Y is gonna be input here. So this one, X, W, Y. So this one, X, W, X, Y, Z. And this one also X, Y, Z. So the first 3 is gonna be input to all of them. Okay. This one should select one of them. Select one of them. To do that, look here, to do that, I'm gonna take one enable here. Look how I made it. One enable here and one enable here. Sorry, not this one. There should be one with inverter and another one without inverter to make sure this one is works, the other one is not gonna work. So I don't need to add inverter because you already have inverters. Okay, you will see. So that's what I mean. I'm gonna make this, take this one here, okay, with this one. Oh man. No, sorry, I'm gonna take this one here with this one. You look? So here I'm gonna take this one here and this one here. So that when the input, when this is W here, so that when W is 0, this one is gonna work, this one is not gonna work. When W is equal to 0. When W is 1, for sure I have to enable the other ones, that's for sure. Okay. If W is 1, so now here this is the enabled one and this one is disabled one. Okay. Now I have to enable the 3. I have to enable the 3 inputs. Yeah. Look now how I can add an enable. Okay. Look how I added one enable. Okay. I took another enable here. I took another enable here. I connected to this enable here, as you see here. And this is the enable. Look here. If I put 0, so both of them should be enabled. Now both of them can work. But if I put one here, so this one is not going to work, this one is not going to work. But you have another enable. Okay, I don't need it. So I will connect it and make it enable all the time because I have 3. Look how it is interesting idea. I have 3. I have to enable the 3. I'm going to take 1, give it to W to control which chip is going to work based on the number you have. That's what I did. So here I took 1 enable. Okay. This one here, I took 1 enable. So I took here 1 with inverter and 1 without inverter. I give it to W to select one of them. Okay. The other one, I connected them together and connected to the enable pin. Still have 1 because I must enable the 3. I must enable the 3. Okay. Yeah. So the third one, I don't need it. So I will connect it. I will enable it all the time. So that's why you see here, this one, I'm going to connect it to booster 5 all the time. This one here, I'm going to connect to the ground all the time. Okay. So here, this one all the time, this one is enabled. Okay. This one is enabled. Any questions? Same thing here. Maybe a lot of tricks, a lot of interesting stuff here. Here, I want to create 2 to 4 decoder. Sorry, I want to create 4 to 16. Here, I created 4 to 16 using 3 to 8. Because this number is for 3 to 8. I use 3 to 8 to create 4 to 16. Now, I'm going to use 2 to 4. I'm going to use 5 to 4, you will see right now. So I'm going to use 2 to 4 to create 4 to 16. How? How can you make it simple? I will make it simple. Look here. Again, for 4 to 16, I have W, X, Y, and Z. Is that okay? Okay. So here I'm gonna take YZ, connect them here, and connect them here, and connect them here, and connect them here. So YZ is connected to all of them. Okay? In total, I have 16. But these 16 are gonna come 4 from the first quarter, 4 from the second one, 4 from here, 4 from here. Is that okay? And still the same idea. I need to enable only one of them, and all others should be disabled. Okay? How I can do that? Who's gonna select which one is enabled, which one is disabled? I'm gonna use this one. Oh, can you explain it? Okay, look it. But now, for now, YZ is connected to all of them. YZ is connected to all of them. I'm gonna use WX to select only one to enable. Okay? So that's why you have here WX and you have a decoder. Let's see how we can do it. Very interesting stuff if you understand. So here, guys, look how it works. Look here, this is the truth table. The truth table is here. Look here, guys. This is the truth table. You can see from the truth table here. In the first four, WX is 0, 0. In the second 4, WX is number 1. In the next 4 is number 2. In the next 4, it's number 3. WX is here. That means in the first 4, this one is 1, everyone else is 0 in the first 4. Because the input here is 0, 0, then that means this one is the enabled one. In the first 4 here, this one is the enabled one, because this is the only one that has 1. Okay? In the second 4, when you have here number 0, 1, it's 0, 1. Now here in this 4, 0, 1. So actually, this is number 1. So this is the one that's enabled. So that means the first 4 I will take them from here. This 4. The second 4 I will take them from here. Next 4 I will take them from here. Next 4 I will take them from here. And only one of them is enabled because this decoder is used for that. This decoder is used to select only one of them to enable based on the 2 inputs we have in the input here. So based on the 2 inputs I have here, I'm gonna enable only one of them. Is that okay? And then, so again, I'm gonna make it very simple. Okay, guys, I'm gonna make it very simple. So when the input here is 0, 0, so that means this one here is I'm gonna select this one, everyone else is off. This is what this decoder is gonna do. Okay. And then here, based on the selection I have here, 0, 1, 2, and 3. So here I'm gonna, in case of 0, 0, so I'm gonna get this one. And then, so this is in case of 0, 0. I already have 0, 0 fixed. These 2 already fixed for all of them. Okay. Then once I have 0, 0, so this is the one that's gonna be enabled. If I have here 0, 1, this one is enabled. Okay. So if you look at the whole number, 0, 0, 0, 0, so this should be D0. Okay. So here, the first one here is gonna be D0. Last one is D3. This one here is gonna be D4. Okay. How is it? How this one is D4? Because if you see here, this part 0, 0, but this one always 0, 1 for all of them 0, 1. Okay. Which is this is number 4. Is that difficult? Make it very simple again. What I'm saying is that in total, I have 16 out. I'm gonna take 4 from here, 4 from here, 4 from here, 4 from here. Okay. X and Y, as you see here, X and Y is gonna select only one decoder at a time. Okay. So here with the input 0, 0 here, for all these inputs, the first decoder is enabled. Everyone else is disabled. Okay. And then based on what value I have here, I'm gonna select one of these 4. One of these 4. Same thing here. Same thing. I'm gonna repeat it again. Same thing here. When this one is 0, 1 here, so this is the one that's enabled. And then based on these 4 values, I'm gonna select one of these 4 and so on. Okay. Any questions? This one has also enable. Look here, which enable I will use? The enable of this one can be the enable of everyone for the whole, for the 4 to 16. Why? Because if this one is disabled, that means this one is disabled, this one is disabled, this one is disabled, so everything is disabled. You got the idea? So this is a master. This is a master. So if this guy is disabled, no one's gonna work, right? So here, this enable actually I can use it the enable for 4 to 16. Okay. If no selection, if I don't enable, because this one is the one that's gonna enable one of these. Okay. Any questions? Okay. I'm gonna leave this one. I'm gonna do and now I'm gonna come to the part I told you about you need in the coming lab, which very easy. Once you understand it. Look here, guys. You can see, as I told you, you can see the decoder, any decoder I explain. For example, this decoder here, guys, listen to me because it's very important. This decoder here, you can see this output like M0, min term 0. So when the input here is 0, 0, 0, this one becomes 1. This min term 0. This one is min term 1. This min term 2, min term 3, min term 4, min term 5, min term 6, min term 7. Now I will explain. If you have a decoder, again, this is not the only way to use decoder. Decoder can use for other things for selection. Similar to the last example I explained, the decoder select one of 4. Okay, but anyway, one way to use the decoder to implement any function. Why? Simply as I explained in chapter 2, any function is the summation of minterms. Any function is actually the summation of minterms. Minterm 0 or minterm 1 and so on. Okay. Luckily, I have the minterms here. All what I need just to do an OR gate to your minterms, and I implemented the function. Say it again. As I explained, in sum of product, the implementation of any function is actually the summation or the OR of all the minterms of the function. I have the minterms here. Just add OR gate, and by this way, I can implement any function. Okay, let me explain it. Yeah, that's exactly what I mean. Here, I want to implement the full adder, carry and summation. This is the full adder I explained before. If you have 0, carry is 0, summation is 0, and so on. I want to implement this one using decoder. Okay, let's first look at the carry, for example. In the carry here, so this function is actually, this is the minterm number 3. This is the minterm number 4, 5, okay, and minterm 6, minterm 7. So I can say the carry is actually the summation or minterm 3 or minterm 5 or minterm 6 or minterm 7. This should be the carry. What it means, very simple. What it means if the minterm 3 is 1, carry has to be 1. If minterm 5 is 1, carry has to be 1. If minterm 6 is 1, carry has to be 1. If minterm 7 is 1, carry has to be 1. Anything else, carry has to be 0. Let me say it in a different way. If the input is 3 or 5 or 6 or 7, carry has to be 1. Any other input, it has to be 0. You got what I'm saying? So that's what I can do here. So now look here, guys. So here I'm gonna take 3, minterm 3, because here we have 3, 5, 6, 7, and then also I have to take 5, 6, 7, and then I will input them to OR gate. This one. And now I've implemented the function using decoder. Are you sure you implemented this way? Can you explain? I didn't understand it. Okay, I will make you understand it. Okay. Make it simple. So here. Look here, guys. Okay, look here. When the input is 0, 0, 0, okay? So here in this case, this output is 1, and every output else is 0, 0, 0, and carry should be 0. Yeah, that's exactly what happened here. Okay. Same thing if the input is 1. If the input is number 1, so number 1 is 1, everything else is 0, and the carry will be 0. Okay, so this is exactly what the truth table is telling me. What the truth table is telling me, the carry has to be 1 only in these cases. Any other cases has to be zeros. And that's what the decoder is gonna do. What the decoder is gonna do, if the input is 3, this one will be high, and I will get 1. If the input is number 5, so this one now becomes high, and output is 1. If the input is number 6, this one is high, I will get 1. If the input is number 7, this one is high, I will get 1. Any other number, I will get 0. This is implementation of a function. You got it? So make it simple. If I want to implement a function using a decoder, 2 things now. Number 1, number of inputs for the decoder should equal to the number of inputs to the function. So if I have a function that has 100 input, I have to find the decoder that has 100 input. That's number 1. Number 2, you need to find the min terms of this function, and then use OR gate to connect the min terms to this. That's it. Very simple. Let's have another example here. For example, here in case of summation. Okay, this one has to give me 1 when the input is number 1, number 2, right? And this one is number 4 and number 7, which can you see? Okay, that means I have to get here when the input here in one of these number, S has to be 1, else has to be 0. Okay, that's why I will connect this one to M1. Or output number 1, output number 2, output number 4, and 6. That's very simple. That's difficult. So if I give you any function, you can simply implement it using a decoder and using OR gates. All what you have to do, you have to connect the min terms of this function to the OR gates. That's it. But you have to make sure that number of inputs here equal to the number of inputs of the function. Any questions? Okay. Here, what is the function? Here, what I'm explaining here is actually this is in case the decoder is active high. Is active high. What if it is active low? How I can do it? This is active high. Active high, they are going to give you the min terms, right? But what if it is active low? Actually, what you are going to get if it is active low is actually the inversion of the min terms. So this is the min difference. Here, this is M0, this is M1, this is M2, this is M3. But if it is active low, I will get M0 prime, M1 prime, M2 prime, and so on. Okay. So here, yeah. So for example, this one is active low. So what I'm gonna get here, M1 prime, M2 prime, M4 prime, M7 prime, M9 prime. So how I can get, so I don't have M1, M2, M3. I don't have, I have primes here. Okay. For sure, one way to do it, which is not a good idea. For sure, you can put inverters here to get M1, M2, and then you can use OR gate as I explained before. You can do that, but I have a better idea. So again, one idea here to put inverter in, and then use OR gate. But what I will do now, I'm gonna use, instead of using OR gate, I'm gonna use NAND gate. But how you can use NAND gate? I'm gonna tell you. Look here, guys. If these are the min terms here, M1 or M2 or M3, it is the same thing if you have here M1 prime, M2 prime, and NAND gate here. Do you remember why this one is equal to this one? Yeah, I know. So because if you use De Morgan, so this one becomes M1 prime, or M2 prime, or M4 prime of prime. You got what I'm saying? So I can say here, if your function has the midterms 1, 2, and 3, you have 2 options. I did a simple algebra manipulation. That's why I told you, although we're not going to use algebra manipulation for simplification because it's difficult, but still you need it. So I did simple algebra manipulation. I found this one here is equivalent to this one. Very simple. So let me tell you the conclusion. The conclusion is, if you have M1, M2, and M3, these are the min terms of a function. I can simply use OR gate as I explained. So I have to take them from here and then use OR gate. Very simple. Or if you have here M1 prime, M2 prime, M3 prime, which are the inversion of the midterms of the function. Okay, so these are the midterms of the function. Okay, so actually, this one is equivalent. This one is equivalent to if you use just NAND gate this way. It's the same thing. Okay, so that's why what I'm saying here, make it very simple, very, very simple. Okay, number one. If you want to implement the function using decoder, number one, if your decoder is active high, you need to connect the midterms here, the outputs here, the midterms to an OR gate. If the decoder is active low, you need to connect the midterms to NAND gate. Done. You got what I'm saying? So in both cases, you have to select the midterms. That's okay. But I'm gonna use OR gate in case of active low, active high. In case of active low, I'm gonna use NAND gate. And they are the same, they are equivalent. This is because the midterms here are inverted. Okay, guys, any questions? Yeah. The one thing I want to explain here is look here, guys. When I tell you S is equal 1, 2, 4, 4, 7, okay? So actually S prime, okay, should equal to the other ones we have here, which is number 3, 5, and 6. Okay? 1, 2, 3, 4, 5, 6. This should be S prime. What it means? Very simple. It means, let me put this way, guys. It means if any one of these midterms is 1, okay, so the function has to be 1. But if not, so that means one of these one should be 1, right? So that means I have to get 0, the inversion of the function. You got what I'm saying? So again, what I'm saying here, if you have a function this way, the other terms, okay, should give you the inversion of the function. And that's actually what we did in K-maps when you product of sum. Instead of grouping ones, we grouped zeros to calculate the inversion of the function. Anyway, you got it? Okay. So what is the point here? What you want to tell us? And what I want to tell you, okay, now, if I can implement the function from here, and that's what I did here, and in this case, I'm going to use OR. Or, if it is, by the way, there is number 0, I forget here. We have also 0. So here, 0, 0. Or, I can implement the functioning from S prime. So that means if I take here 0, and then I take 3, and then I take number 5, okay, and then I take number 6, okay, and then I do OR, this one will give me S prime. Is that okay? Okay, but I can put here inverter, this one will give me S. So conclusion. You can use these midterms with OR, okay, to calculate the function. Or I can use the missing midterms to calculate S prime. But in this case, I have to use also inverter here. I have to use NOR. So I can do it in 2 different ways. If I select this one, I'm going to use OR. If I select this one, I'm going to use NOR. Is that okay? So now it's up to you. Which one is more efficient? You can select. Let me explain it. Here it doesn't matter. In this specific example, it doesn't matter. One, because here I have 4 and 4, 4 and 4. So if I implement this way with this one, it doesn't matter. However, if you have a function, and this function, for example, equal to 1, 2, 3, 4, 5, 6, this way. Okay? So that means f prime should equal to 0, 1, 2, 3, 4, 5, 6, 7. So that means if I implement this function using OR, using this one here, using this one here, so it means I need OR that has 1, 2, 3, 4, 5, 6 inputs. But if I implement here using NOR, I'm gonna only need a function that has only 2 inputs. You understand what I'm saying? So it depends on which one is more efficient. It's up to you. Yes.
Aren't you still going to need the 6 outputs for the carry?
Output number 6 for the carry.
No, 1 through 6
Yeah,
for the carry, so does it really change the efficiency? If you just.
no, because they are equal. So if you look at the carry here, yeah, so for the carry here, I can implement it either using or, and I can input here number 3, number 5, number 6, number 7. Or I can use NOR, and I can input here the missing ones, which is still 4. I didn't make any gain, so whatever you like. So if this is okay, this is okay. There is no one here. I'm talking about the thing here you should understand. Number 1, I can implement as a function from the midterm these ones using or I can implement it from the missing ones, but in this case I have to use NOR, right? Because if you use or here, you are gonna get S prime. That's why I need NOR, okay? And then whatever one is efficient, you can select. So in this case, if I use or, I'm gonna have 1, 2, 3, 4, 5, 6 inputs. But if I use this one, I have only 2 inputs. So this one is more efficient. So here I can use NOR. I can use NOR here with 2 inputs. Any questions? Okay. So in the coming lab, the first part of the lab is actually you are going to use this decoder. I already explained this decoder. So here in the coming lab, guys, very easy. One of the easiest labs you will have. So you are going to use this chip. I already explained how this chip works. Number 2, you have a function. I'm going to ask you to implement this function using NAND. Okay, very simple. So you have to take whatever you have here in the output and you have to connect it to NAND. Okay, because this is active flow. Any questions? Okay. We still have 3 minutes. The second part of the lab is about multiplexer. I explained here multiplexer, so how multiplexer works and so on. But the part here I want to explain also you need it in a lab. You are in the coming lab also. You have a chip that has a multiplexer. Okay, this is a symbol we are using for a multiplexer. So we use, if you have a multiplexer, for example, 8 to 1. So we use a symbol like this one. Okay, you have here 6 inputs. Sorry, you have 8 inputs. You have 3 selectors. You have 3 selectors. So this one should be 2 to the power of 3. Always you have only 1 output. And based on the selection you have here, you are going to connect the output here or here or here or here. Makes sense? Anyway, so how can you implement the function using multiplexer? This is a very naive way. Look at the idea. Very simple. This is a very naive way. Look here, guys. I know when the input is 0, 0, 0, I know the output will be connected to this one. Okay. So what I'm gonna do here, I want to implement this one here. Okay. So when the input is 0, 0, 0. Okay. So the output has to be 0. Okay. So I'm gonna put here 0 so that I get 0. So anyway, so here I'm gonna put in the value of the function. This is a very naive way. So that when the input is 0, 0, 0, the output I will get is gonna come from here. So I can just put here the value of the function. So when the input 0, 0, 0, I will get 0. So I'm gonna put here 0. Okay. When the input is number 1, I want to get 0. So I know, I think this, I'm sorry, this is for the summation. So I know the output has to be 1. I know when the input is number 1, it's going to be connected here. So I'm going to put here 1 so that I get 1 here. Okay. When the input is number 2, okay. So here is the output is going to be connected to this one. So what do you want? This is the midpoint. The midpoint is that when you have a certain input, the output will be connected to one of these. What do you want for this input? Do you want the output to be 0 or 1? Just put it. This is a very naive way to do it. Okay, it's inefficient, but this is very naive way. Okay, so that's why you see here, guys. Here I just copy. I copy this one. I put it here. Okay, so that when the input, for example, number 7. I will get this one, which is similar to this one here. When the input is number 5, I will get this one, similar to this one. Is that okay? Same thing here. You have also a carry, and you have a carry this way. Sorry, this one here. So it's the same thing here. I just take this column, I just repeat it here. So that when the input is 0, I want to get 0 because this is 0 here. When the input is 1, I want to get 0. That's why I put 0 here. Because I know in multiplexer, when the input is 1, it's going to be here. When the input is 2, I want to get 0, because it's 0 here. When the input is 3, it's going to be here. So I have to get 1, because this one is 1, and so on. Is that okay? So again, what I'm explaining here is, I explained what is multiplexer. Okay, for sure I will continue teaching this part, but here what I'm teaching here is, if you want to use a multiplexer to implement a function similar to what I did in the decoder, this is a naive way to do it, okay? Or it's a simple way to do it. Just I'm gonna put here the value of the function. I know when the output here is equal to number 6, the output here will be connected to number 6. So whatever you want here, what the function is telling you? The function is 0 or 1, you can just put 0 or 1. Yes.
So you need 2 multiplexers to do summation or addition?
No. Yeah, in this case,
For some.
yeah, because this is every function, these two functions. So I need one multiplexer to this function and one multiplexer to the other function. Yes, this is a very good point. Yeah, so here, if you use multiplexer, I need 2 multiplexer, but when I use the decoder, I use only one decoder to implement the 2 functions. You can have seen, yes. But anyway, so next time I will teach you here. This is a very, I told you this is very naive or very simple idea, because the problem here, when the function has 3 inputs, I need a decoder that is 3 to 8. Sorry, 8 to 1. 8 to 1. 8 to 1. Okay. Next time I will show you how can we do some tricks so that I can implement the same function here, but instead of using a decoder that has 3 selectors, I can do it using only two selectors. I will do a trick. But this is the simple way. The simple way is the function, whatever that I have here in the function, I can put it here. Whatever you have here, you can select whatever output you get. This is a simple way. But next time I will show you how I can do the same thing, but using a smaller multiplexer. Smaller. Instead of 8 to 1, I can make it 4 to 1. Okay. I think we have time. Oh, okay. Thanks, guys.